It's a great pleasure for me to introduce to you the geodesy section Bowie lecturer, Gilles Peltzer. Gilles Peltzer is presently at UCLA, more precisely Department of Earth and Space Sciences, University of California, Los Angeles. Gilles Peltzer studied in France at the École Polytechnique of Paris, where he made his undergraduate degree. Then he was doing research for the CNRS at the Institut Physique du Globe in Paris from 1983. He got his PhD in 1987. His PhD dissertation was on India-Eurasia collision zone, and it was under the supervision of Paul Tavernier at IPGP. He was going research at IPGP for a few more years than at the Observatoire Midi-Pyrénées in Toulouse, in France, with a 2-year position at JPL Caltech in between. From 1993, he became a research scientist at JPL, and from 2000, he was nominated professor at UCLA in the Earth and Space Science Division. In these last few years, his work was focused on the studies of surface deformation associated with earthquakes using the technique of SAR interferometry. SAR stands for synthetic aperture radars. SAR produces all-weather, days and night, high-resolution images of the Earth's surface, providing useful information about the physical characteristics of the ground. By combining 2 or more SAR images of the same area, it is possible to obtain surface change map with unprecedented precision and resolution. Gilles Peltzer has used this technique to study, in particular, co- and post-seismic deformation of earthquakes in California and Tibet, as well as inter-seismic deformation associated with active fault in these regions. Presently, Gilles' primarily research interest is to study crustal deformation processes from continental scale to earthquakes. He has been using various approaches to explore some of the many aspects of the subject, including scale modeling of continent collision, remote sensing from Landsat, and spot images, fine topography analysis of faults, curves, and application of SAR interferometry to the study of earthquakes and associated processes. His work has been well recognized by the scientific communities, as shown by the list of publication in peer-reviewed journals, and he has a recognition of exceptional scientific achievement. He received twice an ESA medal. Today, the AGU Geodesy section recognizes Gilles Peltzer, the 2002 William Bowie Lecturer. The title of his lecture, Tower Imaging the Earth's Surface in 4 Dimensions. Gilles, you have the floor.
Thank you very much. Thank you very much. It's a great pleasure to be here. So, in the last 30 years, satellite images have been playing a crucial role in the study of active faults and earthquake processes. Here on the top, you have a Landsat image acquired in the 70s of northern Tibet, and these images were used to map very large structure, very large active faults across big pieces of land, and here for the collision between India and Asia, it has been very useful. 10 years later, higher resolution system like the system launched by the CNES, the SPOT satellite with a resolution of 10 meters, allowed scientists to measure lateral offset produced by these faults. Here's the trace of the fault, and the terrace riser here on the edge of this fan is offset left laterally. So they could start to do kinematics with these high resolution images. Another 10 years later, a different product came on the market, and this is a radar. And the radar do not here as it's shown on this image, it's not an image of the ground per se, it's an image of the displacement of the ground, and I'm going to talk about that today. I also want to mention very high resolution systems that are flying now, like the Iconos system with 1 meter resolution, which is allowing you to see rupture produced by a single earthquake. Here the very thin line, which is the dark line, is the rupture produced by the 2001 Kokoshi earthquake in China. And here you see a long-term offset of a terrace riser similar to this one here. But my talk today will be about ITM3 on this image. Doesn't work. So the plan of the talk will be what does SAR interferometry measure, and then I will go through a few examples. Many of them will be in Southern California because we have a lot of data and a lot of ancillary data to compare with. We'll start with a little review of what has been done about the Landers earthquake, the co-seismic study and the post-seismic study of the Landers earthquake. Then briefly go through the Hector Mine earthquake, see the difference between these two earthquakes and the type of study that has been done, and look at interseismic processes in Southern California and especially in the Eastern California shear zone, and finally talk a little bit about what's going on in Los Angeles. So a SAR is a side-looking system which is producing images as shown here on the right side, and the dimension of these images are azimuth, which is the distance along the satellite track, and the other dimension, which is the perpendicular dimension, is the range, which is in fact the distance between the ground and the antenna. Because the image is constructed using the phase of a radar wave, this distance on each pixel of the image is known very accurately. And SAR interferometry is exploiting these measurements to derive a topographic map and displacement map of the surface of the ground. If you image one region on the ground with two images of the same area, you can compute the difference between the two phase fields, between your two images, and if the images are acquired from slightly different position in space or in air, you have a small parallax between the two lines of sight, and that small parallax makes that the phase difference is going to be sensitive to the elevation at the surface. So you can, and this is shown in this equation here, you have a term which includes the topography of the terrain. So you can derive topographic map. If your two images are acquired at two different times, and if the ground moved in the direction of the satellite during the time span by these two acquisitions, the phase difference will be sensitive to a displacement term here that will actually measure the displacement of the ground into the direction of line of sight. So the processing which is involved in SAR interferometry consists first in computing the phase difference, and then to separate these two terms, the geometric and topography term, and the displacement term. I'm not going to talk about that today. We've heard a lot about during the previous sessions about this technique. I'm going to show results that have been obtained with this technique. So, to summarize, the InSAR measures the topography as seen here on the left side, and it also measures ground displacement as seen here on the right side. This is a typical way of showing these displacement or topo map, which is called interferogram, and the fringes or the color here on the left shows the elevation, and here on the right side the topography has been removed from these phase fields, so the color here indicates the displacement in the line of sight of the radar. For a topo map, the rate of the fringes, if you wish, is sensitive to the baseline, which is the separation between the two orbits, which increase the parallax angle, and it is also sensible to the wavelength of the radar. And this is a topo map generated with two different systems, one with an L-band, 24 centimeter wavelength, the other one with a C-band, 5 centimeter wavelength, and you see that the fringe rate is different. However, for change map, once you have removed the geometric effect and the topography effect, the fringes are only dependent on the wavelength, which is here for the ERS system, C-band system, a wavelength of 5.3 centimeters. So when you go from blue to blue, for example, here, you move towards or away from the radar by half the wavelength, which is 28 millimeters. But the interferometric phase is also very sensitive to the distribution of little scatterers on the ground. And there is another information you can use for the study of earthquake or other type of studies, which is the correlation between the before and after images, statistical correlation between the phase. And in urban area, usually the correlation is very good. A yellow color here in this map show high coherence between the two phase fields. And it has been used here in the case of the Kobe earthquake to study regions where there were extensive disruption on the ground, such as demolition of buildings or produced by liquefaction or destroyed by fires. And this has been used in the case of Kobe. On the right side here, it's another interesting application of this quantity. We're not looking at a pair spanning an earthquake. We're looking at 6 months after a large event in Tibet. And here it's a field picture of the rupture. You see that the earthquake produced extensive disruption on the ground. And what you see in the coherence image in the 6 months after the earthquake is the degradation of that fault scarp by erosion. And that shows very nicely as a very thin little line here of decorrelation in the phase. And that, not surprisingly, fall exactly on the Holocene scarp that you can see on the amplitude image of the radar. A little bit of history. SAR interferometry was initially developed for the Earth observation for the first time by the team of people at JPL, including Gabriel, Goldstein, and Zepker. And they used SEASAT data of the Imperial Valley area, which is shown here on this amplitude image. And they were hunting for small earthquakes that were supposedly captured by their data. But the earthquake was too small and they couldn't really see any signal associated with it. However, in their change map, which is shown here, they could notice that these fields were moving up and down, and that was readily detectable in the data. And they correlated these events with episodes of watering of these fields, and their interpretation that the soil was swelling due to the watering. They could also show that by averaging the phase over these fields, which were flat, they could beat down the noise to a level of 0.6 millimeter of displacement. It's extremely accurate. That was published in JGR in '87. Nobody really paid attention to that studies because who cares about the swelling of the fields? But all the techniques was here, and it was ready to be used for an earthquake. Unfortunately, SEASAT died after 3 months of operation, and no data were acquired. It is until the Landers earthquake in 1992 that hit Southern California, which was imaged by the European Space Agency ERS satellite, that the first co-seismic image of an earthquake was done. And this study was done by a group at CNES led by Didier Massonnet. And on the right side, you have the displacement field produced by the earthquake. On the left side, fault model done by an elastic dislocation model. What was actually stunning when these images were published is that first, that radar was capable of measuring the Earth's surface displacement with such an accuracy, but also what amazes me a lot was that with a very simple elastic half-space model, you could reproduce very precisely what the earthquake would do, and that the crust would behave actually very elastically, if you wish. But there are differences between these two images, and this is where the real science was starting. These data have been analyzed over and over, and obviously a lot of details, as I just said, were shown in the data that were not modeled. And you can see here on this example, the little aftershock that hit in December is shown here. And also there are obviously some shear localized on the fault parallel to the main rupture here that was also revealed by these data. But what was more interesting was what was the surface of the ground doing after the earthquake in the post-seismic period. And here we're looking at an image spanning the period between September '92 2 months after the earthquake until January of '96. So it's spanning almost 4 years or 3.5 years after the earthquake. So you see that there is a large signal, large pattern of deformation, but also a lot of deformation along the fault, and I'm going to comment a little bit on that. First, there is well, these large lobe, which resembles what we've seen in the co-seismic displacement field, but with a much smaller amplitude, and that has been interpreted as being either due to afterslip or visco-elastic relaxation or Poro-elastic rebound, and I'm going to talk about that later in the talk. Another feature which is striking here is the concentration of strain on the step over of the fault here, and an interpretation of this is the Poro-elastic rebound. And I'm going to also mention that, talk about that later. This is the aftershock that occurred in December '92. And finally, very clear on the interferogram is when the displacement reached the surface that produced a sharp cut in the displacement field. And this was recognized here along the Eureka Peak fault, which is creeping at the surface. So I'm going to start with the step over here, and I'm going to show you a zoom on this area where there is a post-seismic strain. And what was very surprising in this step over, which is a pull apart here, it's a perspective view of the interferogram, and this is the Jonsson Valley fault and the Homestead Valley fault, and they're making a right step. It's a right lateral fault system, so it's a pull apart, and there is a relay in between, which is the Kickapoo fault. And in between here, as you can see in the shaded view of the phase field, this is the same data shown in 3D perspective view, shaded. There is a net uplift of the ground between these two faults, and the uplift here almost reached 5 centimeters in the 3 years spanned by this data set. On the other hand, in the compressive jog, which is farther north along the fault, what we see in the radar data is there is a subsidence. The displacement is moving away from the satellite, and it's interpreted here as due to a subsidence. You see also some smaller scale features along the fault trace here. That was kind of surprising because when you know that the displacement at a pull apart is going down during an earthquake, and in a push up it should go up, but was exactly opposite to what was seen during the post-seismic period. The model that was proposed that it was a rebound due to a Poro-elastic response due to the co-seismic stress change. And the idea is the following. The upper crust is a porous medium with fluids, and when the earthquake hit, there is a sudden stress change, and the crust reacts as an undrained material. And as time passes, the gradients in the pores dissipate, and the residual strain, which is observed after some time, is corresponds to the drain situation. So because the undrained Poisson's ratio is always larger than the drained Poisson's ratio, the subsidence that you observed right after the earthquake is larger than the one that you observed some months or years after the earthquake. So there is a kind of recovery. And this would explain very well why in the pull apart the ground would go up after the earthquake. That's the recovery when the fluid is sucked in, and in the push-up you would observe subsidence because the water would have to be evacuated, and then the ground would move down. That can be modeled very easily if you have a co-seismic slip distribution, and this is taken from the detailed work of Sowers et al. In this area here. You can generate 2 co-seismic models with different Poisson's ratio, compute the difference, and then sure enough we have an uplift which corresponds to this. The value we use for that model corresponds to these numbers, 0.24 and 0.35 for drain and undrained Poisson's ratio respectively. High Poisson's ratio and drained Poisson's ratio are consistent with fast VPVS ratio in fault zone, so this is consistent with seismology. Now, these images were also showing very large patterns that were resembling the co-seismic pattern, but with a much smaller amplitude. And based on GPS data collected along the transect here, it has been proposed that this was the result of afterslip on the deep portion of the fault. And that was actually matching very well the GPS observations. So the GPS observation were shown, the transect here is shown here with these little white dots on the left panel, and the horizontal arrows here showing the horizontal displacement predicted by this afterslip model. And these arrows were actually matching well the horizontal displacement measured with the GPS. However, the colors here are showing the prediction of line-of-sight displacement for that model. And you can see readily that it's exactly opposed to the color you see in the radar image. It's blue on the upper left corner, it's yellow on the upper right corner, it's opposite to that, and similar in, a little bit different, but similar in the south. So it was exactly the opposite sign. So we proposed at that time that maybe it's a combination of two things. We have afterslip on the fault and Poro-elastic response. After all, there's no reason why Poro-elastic response would occur in the fault zone itself and in the step over of the fault, and not in the country rock on both sides of the fault. Before the earthquake, this is the same material, essentially, and there are fluids everywhere. They should respond to that co-seismic change. So we did the same calculation to a co-seismic model, make the difference with the drain and undrained Poisson's ratio, and we adjusted the value to try to match what we saw in the SAR. And when you do the sum between these afterslip model and the Poro-elastic model, the sum looked really like we saw in the SAR. It means it's yellow on the left side and green or blue on the right side. And the horizontal field continued to match the GPS data. And I can show that in profile here. The noisy line is the SAR data. It's a cross-section of the phase field along the transect. And the afterslip model alone is the dashed line, so you see that it's exactly opposite in sign as the observation. The dotted line is the Poro-elastic rebound only, and the thick line is the sum of the two. Obviously, it has been adjusted to match the amplitude, but it's a reasonable way to interpret this. If you look at the horizontal component and compare with the GPS data, you see that the fault parallel displacement here is also matched relatively well with the combination of the two models, but the fault perpendicular motion is really improved. The dashed line here has a significant departure in the middle of the plot here near zero, near the fault, and by combining this with the Poro-elastic model, it goes much better closer to the data. Alternatively, another way to explain these long wavelength pattern, or spatial wavelength pattern, is to invoke visco-elastic relaxation. And this is a study done by Fred Pollitz and co-workers. And they argue that if you want to reconcile what you see in the SAR with what you see in the very far field here in the GPS data, there were stations pretty far from the fault, actually more than one fault length from the fault. And this site seems to continue to move pretty fast, at very fast rate during the year following the earthquake. And to be able to explain this, they argued that visco-elastic relaxation with a relatively weak upper mantle was necessary. And this is the model they produced, and it actually explained relatively well the long spatial signature of this interferogram, probably better than the previous model, but it doesn't explain the short wavelength features, the steep gradient we had at the fault. So it's possible that there is a combination of all these processes. So we're left with a series of processes that apparently are dominant in some places. Afterslip must occur to explain the very steep gradient we see at the fault, and it's absolutely evident in some places like the European fault where it's creeping at the surface. Poro-elastic rebound seems to be a reasonable explanation for what's going on in the step over. That explains very well the difference in sign depending it's a compressive or extensive jog. And bulk visco-elastic relaxation needs to be advocated to explain the displacement in the very far field of the fault. These processes occur at different time constants, And obviously, these time constants are not very well resolved in our data because we do not sample the time dimension very well. I want to show something you have seen earlier in the session in this room, is the work by Jonsson and others, and it's the PhD of Jonsson. These are post-seismic studies of 2 earthquakes that occur in southern Iceland. And on the top here, you have observation with radar data on both descending and ascending passes of the radar. And these are very short period of time. We're looking at 35 days, one cycle of the satellite. And there is a very large signal which shows 4 quadrants similar to the one you see along these track slip events. And the model that they proposed was to explain that solely with the Poro-elastic rebound. And their main argument is the very fast decay time, and in 35 days to have such a displacement signal, it's difficult to explain that with other processes. And I found this a very interesting case to show that in that case there is a strong argument to say that Poro-elastic rebound play an important role in these post-seismic processes. Then 7 years later, the Hector Mine earthquake hit the Eastern California shear zone, taking by surprise many people because the epicenter of the Hector Mine earthquake was very close to the shadow area, stress shadow area produced by the Landers earthquake. So there were different models to explain why these 2 earthquakes occur. This was an ideal case in a sense because we're lucky enough to have an image taken right before the earthquake occurred, and 4 days after. The European Space Agency responded very positively to the swamp of requests that came to them, and they put their radar on, and we had these wonderful images with excellent coherence and actually a good orbit configuration in that case. So these data were really analyzed in detail, and in 7 years you can tell that the computational computer and software arsenal really improved, and the studies were a lot better and refined. I want to point out here a study done by Fialco and others who used ascending, descending orbit, line of sight displacement, as well as what we call offset displacement. This is just an offset you can measure by correlating the amplitude image along the azimuth direction to recover the 3 components of the displacement field, and from that invert from the up, east and north component of the displacement field. So this is the first time that a continuous 3D displacement field was ever made after an earthquake. They also look at the descending data very, very carefully, and this is a complicated image. It's a shaded view of the phase field after high-pass filtering. So the long wavelength produced by the main earthquake are gone, but what you see here is the short wavelength signature, and you see some kind of depressions in this rendering along adjacent faults parallel to the main fault. And their interpretation was that it was due to a backward slip on these faults, and that was due to the response of weak faults to the change of stress produced by the main earthquake. That was a very detailed analysis of the displacement field, and only made it possible by the fact that this view of the displacement field at the surface were continuous with InSAR. But of course, this earthquake continued to produce things after the main event took place, and in the month and years following the earthquake, all these processes of relaxation started to occur. And the difference with Landers is that data were acquired immediately after the earthquake. As I said, the co-seismic image was produced with an image acquired 4 days after the earthquake. It means that the data in the post-seismic period capture the immediate post-seismic response of the crust, and that was a big difference with Landers. Pollitz et al. Explained the pattern that they saw in the post-seismic data using a visco-elastic model, as they did for landers, and they ruled out the after-slip model because again, the same thing, the 4 quadrants were actually exactly opposed to the sign observed in the post-seismic data. I'm going to show you on the next slide profile here along the fault and parallel to the fault, crossing the 2 peaks of their displacement model. And with the 3 interferograms that you saw before, the one in the first month after the earthquake, the one from 0 to 8 months, and the one from 1 to 9. And they couldn't fit very well their data with a model using a single viscosity value. So they had to advocate variable viscosity to explain that. And this is the whole discussion of the paper, is to say that the viscosity started with a very low value and increased from 3 to 8 between the -0 and 9. And the trend here is consistent, according to this author, with the value observed at landers using a 3-year post-seismic interferogram. The value observed at landers was on the order of 10 to the 19 Pascal seconds. So that was a very careful analysis of this data set. However, I want to point out that these people ignore the Poro-elastic component of the response of the crust, and it is possible, because of the resemblance of the Poro-elastic signal in map view with these 4 quadrants and the Visco-elastic pattern, that the combination of Poro-elastic model and Visco-elastic model could be an alternative explanation of this apparent variable viscosity here. If these processes occur at different time constant, then that can be that can produce this kind of pattern. So ERS was launched in '91. The first ERS satellite was launched in '91 and started to image Southern California in '92, right before the Landers earthquake. Actually, there were only 1 image before landers acquired by this satellite. That was extremely fortunate. But in 10 years, there is a very dense and populated archive of data over California. And we've been trying to see whether these data could be used to do interseismic geodesy and to measure interseismic deformation of things were not related directly to earthquakes. So we looked at this area here, which is between the which is west of the zone affected by landers and Hector Mine. It is an area crossing the San Andreas Fault, the Gallup Fault, and going into the area between Owensville and Death Valley. In 10 years, between '92 and '91, of course, there are the deformation associated with 6 earthquakes, started with Joshua Tree, Landers, Big Bear, then Northridge, just west of this thing, in western Los Angeles. There's 2 earthquakes, small earthquakes in the Ridgecrest area, and more recently in '99, the Hector Mine earthquake. During these 10 years also, Los Angeles moved something like 24 centimeters to the northwest, with strain accommodated essentially along the San Andreas. And all these faults here in the Mojave moved by smaller amount, probably 5 or so millimeters per year for the Gallup fault based on geologic studies, and with much smaller rate for the faults within the Eastern California shear zone. So the approach here was to assume that all these long-term rates were uniform during the observation time, the 10 years observation time, and to do a combination of these data by just averaging the data. And the reason why we do that was to bring down the noise in the satellite images to start to see very slow processes. And what you see here is an error map, or an assessment of the error, based on a jackknife procedure from the series of images we used for that average map. This procedure consists in removing 1 by 1 each image in the stack and compute the standard deviation, the RMS, if you wish, of the n average map that you produce by that to see the sensitivity of contribution of error of one image one at a time. And by doing so, you come up with a confidence interval map. So you can see here that the scale shown here is very small. We're going from 0 to 0.5 millimeter per year. All the map is essentially blue, and there are zones where these error seems to be a little larger, and these are areas where the assumption of uniform rate in time is not correct. And this is the case in Los Angeles, where, as we'll see later in the talk, there is a lot of processes going on, seasonal breathing of the surface due to water pumping and injection. And that area here probably corresponds to the signature of the post-seismic deformation after landers, which landers occur somewhere here, east of this track. And obviously that is due to the water pumping in the Lancaster area. But overall, we come up with an error which shows on the order of 0.3 millimeter per year, which is very small. So we can start seeing things. But before going into the Mojave, where we don't have GPS data, we have to pass the GPS test, and that's what we did across the San Andreas Fault. And this is the velocity map, which comes out from the stack. And it's in millimeter per year, 20 millimeter per year, line of sight displacement. So what you see here is that Los Angeles is yellow, the Mojave is bluish or purplish. So there is a plate motion here. You see the motion of the along the San Andreas Fault. The Pacific plate is moving to the northwest, and the strain is accumulated in the vicinity of the fault. This is a profile shown here on the left. And the shaded zone here is the collapse of the interferogram into a profile. We collapse the entire scene onto a profile. That's shown here. And the dots here are the SCAG velocity GPS solution. The solid line here is an elastic model based on the SCAG velocity solution. So there is an excellent agreement between the two data sets, and we can say that SAR passed positively the GPS test in this case. You see in Los Angeles, the SAR image is more bumpy, and again, this is due to subsidence, and we're going to talk about that later. So now, let's look at an area here farther north in the Mojave where we don't have as much GPS and where we have active faults, the Garlock Fault and the Eastern California Shear Zone faults. If you go on the SCAG webpage and you click on these faults, you can get long-term rates on these faults based on geological studies. And the Garlock Fault is known to creep at a rate of about 7 millimeter per year. That's a preferred rate based on the shoreline, offset shorelines near the Sears Lake. And the faults in the Eastern California Shear Zone, which has been identified after or before landers, actually, as a wide shear zone, about 100 kilometers wide, going from the eastern part of the Big Bend along the San Andreas into the Owens Valley, Death Valley zone, a shear zone where about 15 millimeters per year of right lateral shear is accommodated in a 100 kilometers wide zone. And this fault is comprised of many faults. Two of them have produced earthquake recently, the Hector Mine and Landers earthquake in the south. And in 1872, the Owens Valley earthquake ended somewhere here. So it's recognized shear zone here. So this is the same data set as we've seen before, but we're looking at an area which is not moving as much as Los Angeles across the San Andreas, so we increase a little bit the sensitivity here. Our scale is 10 millimeters per year. So there are a number of features you can see in this picture. First, the coastal volcanic area, where there's a lot of geothermal activity here in the north. You see also subsidence around the dry lakes, which is due to change in water level on the ground, and the effects of these earthquake crises in 94 and 95 here near Ridgecrest. But what is striking here is the change of color along this line. The upper corner here is doing something with respect to this lower corner here on the left. There is shear along this zone. And this is one of the faults, which is the Blackwater, extending into the Little Lake fault system into Owens Valley here. If you do collapse a cross-section across the space field. That's what you observe here. The blue dots are all the pixels in the image collapsed on the vertical plane perpendicular to the Blackwater Fault. And you see that, well, it's kind of noisy, especially because we collapse the entire scene. It's not a narrow profile. But there is clearly above the noise a step here, concentrated here along the Blackwater Fault. And these lines show the SCAC model without the Blackwater Fault. Long dash is the SCAC model with the Blackwater Fault added, and that seems to reasonably well explain what we see here in the data. And to produce this curve, we used a model with 7 millimeter of right lateral shear along this fault and a locked depth of 5 kilometers, which is amazingly shallow. So there is evidence for right lateral shear along this zone between the northern tip of the Landers earthquake and the southern tip of the Owens Valley 1872 earthquake in Owens Valley. And this is seeming to link the two rupture zones. Another thing which is important here is the agreement with the GPS data. These data were collected by Gann and others from the USGS here just north of our imaged area. And it's amazing to see the agreement between the direction of our shear zone and the arrows here of the GPS. And not only the direction, but the amplitude of displacement across that shear zone seems to agree extremely well here. So there is strong evidence of right lateral shear in this fault. So what's going on? The geologic observation and geodesy before 92 tend to suggest the following picture. There is a distributed shear along the Eastern California shear zone across the width of about 100 kilometers, and this shear occurs at a rate of approximately 12 to 14 millimeters per year. There are numbers that differ quite a bit. And this shear is an explanation of the gradual bending of the Garlock Fault as you go east along the fault. What the SAR data seems to show is that the Garlock Fault doesn't seem to move very much. Actually, when we produced this image, we were seeking for creep on the Garlock Fault or shear on the Garlock Fault. We didn't see any. Resolvable by the SAR, I think it's possible that it should be below the 2 millimeter level, but certainly not 7 millimeter per year. And there is a concentrated zone of shear along the Blackwater Little Lake Fault. So is this post-seismic transient, post-seismic post-Owens Valley Landers? Or is this a longer-term process which involves stress transfer between conjugate fault? This is the Blackwater Fault, this is the Garlock Fault. They are conjugate systems. They intersect one another, and stress must be transferred from one fault to the other when one fault is picking up in activity. The data that we have in hand now do not allow us to answer these questions. We need, obviously, a denser time series and a longer time series. When I say a longer time series, is not only a time series of geodetic data, because obviously these processes, if this is stress transfer between faults, would take place over time periods of hundreds of thousands of years or even more. And obviously the time series that would be needed involve geologic observation, cosmogenic dating of offset features along these faults, and so on and so forth. So we're looking at a big picture here. Conjugate faults exist in nature. This is a picture taken by Paul Taponnier somewhere over Iran in the 70s. And these are anticlines, and they are offset nicely by two conjugate faults. For those who didn't see them, this are the location of the fault. And this is very consistent with the uniform stress field, which is transect to the image here. But these faults have to do something peculiar here, but unfortunately it has been covered with these young sediments, and we don't see anything here. So what's going on? So we go to these famous Plasticine experiments, and we see what conjugate faults do. And as you see in a sequence like that, obviously these faults cut one another, and there are phases where one is active, the other one is dormant, and this oscillate between the two faults. So is that something we can start to see in the data? That's a question that could be answered if we had a really long time series covering this region. I want to mention something that Jeff King pointed out to me. I didn't know that paper. I think this plot is amazingly, it is very impressive. This is Anatolia, this is Turkey, and the North Anatolian Fault and East Anatolian Fault. And Ambrase in 71, Fourth Anatolian Fault. The East Anatolian Fault was not active. When the North Anatolian Fault was dormant, this Eastern Anatolian Fault was picking up, and these are accounts of damaging earthquake along these two faults. There is a pattern of oscillation between these two faults here, and that may be what we see in the Eastern California shear zone. I want to mention also something that has been presented earlier in this AGU by Mike Taylor, which is recent results in central Tibet. Here, as you know, there is a right lateral shear zone, which is called the KGFZ, which is going from the western axis to the eastern axis, and it's formed of en-echelon right lateral steps. And north of this fault, there are left lateral faults that are coming, and these are producing conjugate structure. This is a SAR image covering one of these left lateral fault, and this is a 6 years interferogram, and this is a cross-section, a collapse of this entire phase field perpendicular to the fault, and this is a textbook example of locked fault at depth, locked fault at the surface creeping at depth, and that can be matched with a model with 5 millimeters per year of slip and a locking depth of 13 kilometers. Obviously, this rate is very high, especially when you compare it with the recent rates that is published from GPS studies along the Altintag Fault. The first paper came with a rate of 9 millimeters per year, and more recent results in eastern part of the fault indicate that it could be even lower than that, on the order of 6 millimeters per year. And obviously, the Altintag is a much more important feature in the collision zone than this little fault here. So obviously, if you project these rates in time and say, well, this is the long-term rate, and we're going to explain the history of the collision zone with these rates, you're going to come into incompatibility. Obviously, you cannot sustain such a fast rate and such a slow rate on the Altintag over millions of years. Now, the last part of my talk will be a little LA story. This is Los Angeles here, the San Gabriel Mountain, the San Andreas, and wrapped on top of this USGS DM. This is the average velocity map that you've seen before. And as you know, there is a lot of interest in LA to understand how the strain between Palos Verdes Peninsula, which is moving north with respect to the San Gabriel, is accommodated throughout the city. However, as it has been recognized earlier, Los Angeles is an urban area. There are many people living there, and they drink and they water their lawn, and they need water. So they pump water in the ground, and that's produced these huge subsidence holes, and this is the deepest one we've seen. It's about 15 centimeters of subsidence here in the Chino area. But there are other places where these patterns are very obvious here, and that has to be taken into account in any measurement you do. And that led the team, led by Gerald Bowden from the USGS, to analyze the SAR data in detail to see how this subsidence-induced displacement could corrupt the measurements done with the GPS. You know that in Los Angeles there is a permanent array installed, and these data are analyzed to measure the strain throughout the basin, and if there is some contamination due to subsidence, then you cannot do a reliable tectonic measurements. So they noticed that during the summer season, the ground was moving down. This is shown here on this two panel here in the Santa Ana Basin, and during the fall season, where the rain was bringing water into the aquifer, the ground was moving up. This is a transection of this phase field here between, and the blue line show recharge period, and this line show subsidence period. So they analyzed these data very carefully and decided that some of the sites in the sign area were corrupted by subsidence, and they couldn't be used for long-term tectonics. And they revised the previously published results in this area using the sign data, and one of their conclusions was that there were no evidence of confined contraction in the northern Los Angeles basin. One of the previous results argued that the southern part of the basin was not contracting much, and that all the deformation was located here. And these people say that these data were not supporting this result. However, can we use the InSAR data to help a little bit in this debate here? And this is a zoom in the Los Angeles area of our velocity map. And Brodin et al. Were right. There is a long-term signal here in the subsidence. You can see all these blue-eyes things. And this has to influence the GPS rate. So we need to be careful with that. And what are these things? Obviously, if it's seasonal, it's up and down in the spring and the winter, then that should be removed from that average map. And the reason why it's not removed is that there is a long-term trend here. So here we know it's water pumping. The Chino people acknowledge that. But in the other part, it could be water, but it is oil in some other areas. Oil fields do not recharge in the spring, unfortunately, as does aquifer. That would arrange the affair in the White House, right? But anyway, these are essentially oil fields. This is the Santa Fe Spring oil field. This is the Beverly Hills oil field. And Long Beach area is known for heavily oil pumping here. And again, this is an average map, 10 years average map. So there is a long-term signal here. This plot is to show that our data set sample very evenly the seasons. This is a count of the coverage by month over the year. And in 10 years, we cover essentially 100 times each month, though it's not biased by any seasonal signature, so the seasonal is gone. But can we use these data sets to help estimate the horizontal motion from measured from GPS? And the answer is yes, it's an approximation, but it may be helpful. On the left side here, you have a very simple model of subsidence. You have elastic half space, flat seal underground, contracting, and this is the vertical displacement here produced by subsidence. And the top curve here is the horizontal displacement produced by the same subsidence. And the bottom curve here is the horizontal gradient of the curve in the middle of the vertical displacement, essentially the derivative of this one with respect to the horizontal axis. So what's striking here is that the top curve, which is the one we'd like to deduce from the SAR data, is essentially the mirror image from the gradient of the vertical displacement. And there is a scaling factor, of course, which is alpha here in these equations, and that the alpha is obviously model dependent depending on the depth of the aquifer and structure of the upper layers, and that has to be calibrated. So the idea is to use the seasonal signal observed at some GPS site, and for which we have coverage using SAR data. So we compute the horizontal displacement from the GPS and the gradient from the SAR data and calibrate the alpha number. And this was done by Don Argus, and he's going to show that on Tuesday in this meeting. And the alpha number, I won't tell you the value, come to the talk and you're going to know it. But if you do that, and it was done by Don, you come up with a number of corrections to bring to all these GPS sites. And you see that the correction is very small for many of them, except a few. And in particular, Whittier College has to be corrected by a 3 millimeter per year rate, which is significant here. And the USC site, which was supposedly corrupted, doesn't need to be corrected. And this is because it is going up and down, for sure, but it's in the middle of the depression, so it's not moving laterally. And therefore, it's a reliable horizontal displacement benchmark. So if you use this correction and correct these GPS values, this is what you come up with, a map with, obviously you reintegrate the USC arrow here, but the Whittier College arrow seems to move to the north at quite a fast rate, which was not in the previous map, so reinforcing the idea that this part of Los Angeles is not deforming too much, and this accommodates most of the displacement. So this is in progress, and as you can see, on Tuesday you will see the talk by Don Argus, and he's going to explain all these little details of that study. So, my conclusion, InSAR is changing completely the way people do and will do geodesy to study displacement of the surface. And the main contribution of InSAR compared to what previous system was providing, is the continuous view of the displacement field of the surface of the Earth. And you have seen in these examples that the fact that you could image the displacement continuously would reveal processes and zones of deformation that you would not have expected without this data. It's an ideal complement of GPS permanent arrays, which provide temporal continuity only where these arrays exist. And there are not very many places on Earth where they exist. Los Angeles is one, and Japan is another one. But definitely, it's ideal in these cases, but it's not everywhere. We've seen in the cases of post-seismic studies and in the case of interseismic studies in the Eastern California shear zone that the competitive model or classes of processes could not have been unambiguously identified because of the lack of sampling of the temporal dimension. And definitely this would really help to have a system that would sample the time more frequently. So the future directions obviously is to increase the time. And when I say the time, it's true for a geodetic system. We're talking about a SAR mission that people are working on, who would need a mission with a frequent revisit time and a long life, of course, but also go back in time and look at the geologic record, paleoseismologic studies, studies of quaternary offsets along faults and coast behavior that vary over time constant, which are much longer than the geodetic window of observation of a few decades or for 100 years. And obviously, since you've seen in this AGU that InSAR is growing, there are more and more papers on InSAR, and this is great, and it's now a component of the EarthScope project. I will just conclude by acknowledging all the people I had the opportunity to work with during these last few years, and I would especially insist on the group of people at JPL, including Paul Rosen, Jan Julian, and Scott Hensley, who are really the SAR people here who are really helping in these all these developments. And of course the ECO science team, very enthusiastic people, probably the group of people the most supportive of the SAR mission in the last few years. I definitely had great contact with them. And I finished by the fact that all these data that were shown here, and you've seen in the session this afternoon, were provided by the ERS satellite from the European Space Agency. The European Space Agency did a great job at changing the scope of their mission. Nothing was designed for doing interferometry when they launched the satellite. Changing the scope of that mission on the fly to provide more data and auxiliary data like ephemeris and so on and so forth to help the community to use these data for this application. Thank you very much.
Okay, thank you. We have a few minutes available for questions. Okay, well, yes, Roland.
If you try to put a maximum rate of strain accumulation across the fault, you just try to model it and see how much you can.
Well, when you look at the interferogram collapsed in a profile perpendicular to the Garlock fault, you do not see any resolvable step. It's within the noise, and we cannot argue that it's not creeping at a rate below 2 millimeters per year, which is significantly lower than the geologic rate anyway.
Okay, more questions? I have one. I'm actually very interested in the Conjugate fault case. I mean, in terms of the temporal evolution of this, mechanically, how do you think this really works? Whether the one fault is moving and the other fault moves, how do they communicate which one has the right of way?
Well, we know that when creep or slip occur in one fault, this is changing locally the stress field, and they communicate via the stress. And that's certainly people call stress transfer or something like this, but certainly that's the reason they communicate like that.
Sure, go ahead.
Great talk.
Thank you.
I have a couple questions. Would you remind us what the footprint size is the star? And also, Jeff, I know you're really watching this one. With the Alaska earthquake that just happened recently, it would be really great to get started. But it's very complicated because of all the snow and ice and everything. Could you comment? It's very complicated. What is the probability of change in our thinking?
Yeah, this earthquake occurred at a bad time. ERS-2 is still operational, but it has problems of attitude control, and the European Space Agency is not acquiring much data. I'm sure if they had the opportunity to do so, they would do so for the Denali earthquake, especially because there is a receiving station right there, and it's very easy for them. I don't know what has been done in this field. Maybe you know that.
No, I'm actually not sure how much data has been acquired from the ERS because of the problems with the ERS satellite. I know that a fair amount of data has been acquired from RadarSat. But last week, RadarSat acquisitions were, we hope, temporarily suspended because of, again, some problem with the satellite. They say that they're going to restart acquisitions again in December. I do know from some work that Evelyn Price did as part of simulations and other studies for this NASA Global Earthquake Satellite System that the coherence over one-year intervals is actually pretty good over some of the area, at least, of where we expect the displacements from the earthquake. So if, assuming that the satellites continue to work, then I think we can expect to get some good results, although it may not give results from very, very close to the fault because of the steep topography and the presence of a lot of ice. Okay, do we have maybe one final question? No, okay.
So thank you very much, Gilles, for this very nice talk. President of the Geodesy section, would like to present you with this certificate which acknowledge and recognize your achievements by nominating you as a Bowie lecturer for the Geodesy section. Congratulations.